Mhm, mhm.
Okay. Yeah. Uh, we can start now.
Yes. So I think I had around, I think 80 or so slides right now, 87.
Okay. Too
Um,
many. Let's yeah, let's go quickly with this. Yeah.
okay, so in this presentation, I am presenting articles on deep learning, which are basically being used for anomaly detection research, and I'm going over the past research. So, first of all, what is the high level classification of approaches? As we know, I think we have a few categories that we have already defined, like the unsupervised, the supervised deep learning methods, the weakly supervised deep learning methods, where we have either lesser data or lesser anomalous samples, or we have very little in the form of annotations, or
Okay.
we have, yes. Right. So, and we also have the self-supervised learning approaches where sometimes the approach basically tries to create pseudo labels, or it tries to, perform a different task in order to be able to help learn a better feature representation for anomaly classification.
Okay.
So this is a very high level classification. In terms of the unsupervised approaches, there is a very neat classification in terms of what are the different ways in which they are being tried out. Um, One of the very high level, at a very high level, of course, there are modifications to it. Approaches are the reconstruction based methods, which includes autoencoders. So variational autoencoders also, but autoencoders would be the best example here, and the generative adversarial networks, which basically try to reconstruct the output and input, and basically based on the difference in the input and the output image, the anomalous areas are segmented by the assumption that the autoencoder, which is untrained in an unsupervised manner on normal data, will not be able to produce the the areas which contain the anomalous features. So that's an assumption that's added in reconstruction based methods, which includes autoencoders and generative adversarial networks, which are also trained adversarially. Um, so this is a reconstruction. Then the other ones are distance based methods, basically methods which try to use some heuristics in order to figure out how far a particular test sample is from normal data. So a best example is just doing a nearest neighbor classification, spade or patch score, and they try to do use a pre-trained network representations, pre-trained feature representations from big networks. The other example is likelihood-based distance measures like past dimensionality reduction, which I'll go over a little bit, which try to use like a
Gaurav,
Gaussian.
we don't need to talk about this. We can
Mhm.
skip to the next slides. This is kind of general approaches.
Yes, yes. So this is just a general.
You don't need to list them. Yeah, we don't need to explain them in detail.
Okay. So in the terms of self-supervised approaches, also there is a big general classification. Self-supervision via simulated anomalies, reconstruction by painting, prediction of geometric transformations, prediction of relative positions of patches, and self-supervision
So
during
what's the
pre-training.
key idea of the self-supervised approaches?
What is the?
What's the key idea of the self-supervised approaches?
Yes, so the clear idea of self-supervision is that, okay, we might not have anomalous samples available with us. So, we can't do we don't do a self-supervised training, but using self supervision, such as predicting geometric transformations or trying to reconstruct by in painting, we can either get a better feature representation, or we can basically classify anomalies just as such. So in self supervision, also the ideas that are being used to use self supervision basically differ between the approaches. But self supervision is that, okay, the network is trying to supervise itself using a certain task. So, but of course, the approaches basically differ in the ideas and the basically the reasons for how they are basically
So,
segmenting in all
how
these
does
different.
self supervision? I mean, what's the role of the so-called self supervision? Is it like the algorithm or model will generate the labels by themselves, or
Yes, yes, I think that's a good point. So, in the first case, they do generate labels on their own, where they try to create pseudo labels and simulated anomalies on their own to basically better try to simulate the real world anomalous data. So, they try to create some anomalies and try to learn in that way.
Mhm.
Um, so that's the case with the first one. And definitely, I think in the other ones, also in the in painting one, it's a little bit different. But I think in definitely they try to create in geometric transformations also, they basically try to use a different task where a different, a different label set is present, and through that try to be discriminative on the anomalies. So um, but I think that's a good point in terms of, basically being generating labels on their own and trying to come up with a different task for supervision. Yes.
Okay.
So that's very high level right now. In terms of the data sets, I think that there are different data sets. I haven't added them totally in the basically in the I haven't described them all of these in the articles, but there are many of these just to point out over here. So without domain considerations, like which contain objects from different domains, we have the MVTech and the Visa dataset. Also, there are others that have come out last year uh, in terms of this year basically. In terms of defect data sets with textured surfaces, that's basically considered a different domain for surface quality inspection for defective production items.
So
And for
the MV tag and the visa is about what? It's about cracks or something or whatever. What's about? I mean, what are the examples about?
Yes, yes, I think that's a good point. So on the MVTech data set, basically the defects can be from different categories. So it can be an object like bottle, and it might have a crack, or it might have a missing part, or basically other types of defects. Basically, there are, I think, 12 categories of defects so the number of categories of defects are pre-specified, but there are, of course, more than just the crack. Crack is also a part of a defect in the MVTech category. I have observed some of the images in it. So yes.
Okay.
But it could be like a missing part or like a missing area. So, that's also considered abnormal in this case, like a transistor with a missing, basically like a missing leg or a missing portion. So,
Okay. Go on.
and the Visa also, I think it has defects from for different electronic components and other general like general surfaces like cable, like pills and so capsules and so on. And also there is a distinction between with the industrial defect detection with textured surfaces, which are used for surface inspection, which are coming from the production items like fabrics and so on. Um, Steel also is an example. The steel data set, DAGM, collector, STD, that's surface defect detection,
Mhm.
BTA, yes. and the BTAD and the AI text, and there's the magnetic tile data set also. And in terms of domain specific ones that I was just going over for experimentation, I think one of these is just the aircraft blade anomaly detection, which has examples of basically aircraft blades which are used in the engines. And I did see that there were some examples on Kaggle on basically other aircraft components. I haven't fully gone over them because I wanted to first create the presentation. So I'll see if there are others that can be used. And definitely biomedical data sets like retinal OCT is like a very good example because they use the literature directly on it. They cite the literature on anomaly detection. There are others like brain MRI and head CT, which basically try to also use other methods. So that's like the classification of data sets in over here. Any questions on this? More questions or
Okay, we can go on.
yes, yes. Um, and before I go with the first slide, I think there's also a lot of metrics that are being used in order to assess the performance of the methods. Um, and there are new metrics that came out in the I think one of the articles this year. And most frequently, the normal samples are considered like the negative class. So we say negative sample is a normal sample, and the anomalous sample is a positive class. So that's how we define the true positives, the true negatives, false positives, and false negatives, and their rates. ROC curve is simply a curve showing the plot of the true positive rate versus the false positive rate at different thresholds. AUROC is basically the area under the ROC curve, and a PRO score is
So
given by yes.
AUC, AUROC is calculated based on the classification of each pixel, whether it is anomaly or not.
I think that's basically there are two types of AUROC. So one is the AUROC that's measured at the image level, where we have basically true positive rate and false positive rate for image level detection at image level detection. So if an image is anomalous or not, so that's how it is measuring the true positive rate and the false positive rate, and then plotting the ROC and AUROC, getting the AUROC. Or it could be at the pixel level, where the pixel level is okay. We have the ground truth segmentation mask, and we also have the predicted segmentation mask, and we basically using the how the pixel is classified, we come up with the AUROC score. So there are two AUROCs here which are used for performance uh, at image and pixel level. So
Yeah, this numbers are more like doing classification, right? You're gonna classify each pixel to be in the anomaly or in a normal region or in the normal objects of the original graph, right? Original image.
yes, yes. So it's basically basically a class coming from the classification point of view. So under different thresholds, threshold are basically a little bit specific to the method. So it can be different thresholds for the method corresponding to the method through which they get the true positive. Okay, at this threshold I got these many true positives and false positives, and I just plot it at different thresholds. Like in k nearest neighbor, my threshold could be just the distance, just the distance threshold, and I plot the true positives and the false positives at different thresholds. But it is definitely a classification metric. So it is basically trying to classify what is the probability of if we are given a pair of two samples, which is from the positive and the negative class, then what is the probability that the positive class will get a higher score? So that's something that so AUROC is basically an aggregated answer at various thresholds. So it's not just doing one threshold, but it is basically aggregating the information at different thresholds. So that is one thing I have seen in this task. Yeah.
Okay.
And the PRO score is basically specific to anomaly detection. So it is coming, so it should not be curve here, but it should be the AUROC score considering only ground truth anomalies. So we only take the anomalous region in the mask and we basically try to calculate, okay, how many of the anomalous connected components are true positives and false positives based on the thresholds, and we come up with the AUROC curve, and then we take the area under the curve, which is the PRO score. So this is only taking the anomalous area, which might be a few pixels in diameter on the image, and not considering all of the background areas which are basically in the negative class, because it is a very imbalanced data set for segmentation. So the normal class is how heavily outnumbering the anomalous class, and in this case it is easy for the network to classify the background class but difficult to do the, and so it's more like a hard subset selection case. So we are trying to go try to just take the anomalous areas and calculate the AUROC score through that. So that's the PRO score. It's also similar to basically, I think there would be another metric that can be like the IOU score, that's the intersection over union with just the anomalies. So that can be, but it's basically just considering the aggregated answer for that. So PRO score. And average precision is basically the area under the precision recall curve, which is different from the area under the ROC curve, because ROC curve does the true positive versus false, true positive rate versus the false positive rate. But the precision recall curve does the precision versus recall. Recall is, I think, the recall is basically the true positive rate, and I think the precision is basically the positive predicted value. So that is where it is different. So basically out of all the predictive positive samples, how many of them are true positives? Um, so that's there. And the measure, I think one of the articles did say that it can be useful when the number of false positives are high, but the positive class is outnumbered by the negative class.
Don't stuck at here. Yeah, I basically understand every metric. Just let's just move on. Let's just say the detail works.
Yes, yes. So I'll just go over the next slide.
Mhm.
So, so first article I selected is basically the Spade article, which basically made a big difference in terms of I had added it because it made a big difference. And so, first thing that it does is basically it tries to use representation learning using large pre-trained networks like ResNets. So it used a pre-trained ResNet to extract features for unsupervised anomaly detection. It's a totally unsupervised method, and feature extraction at pixel level was performed by concatenating features from the last M levels of the pre-trained ResNet. Um, so first of all, there is a distinction between the features that are extracted for pixel level task and the image level task. And in this case, the feature extraction at pixel level was basically performed by concatenating features from the last three or four, or it can just be three levels or two levels uh, of the pre-trained ResNet, which has been trained on the ImageNet task. And for image level feature extraction, it uses global pooling from the last convolutional layer in order to obtain image level representation and to do a image level KNN. For a given test sample, if we are given a test sample, the algorithm use the KNN, K nearest algorithm, neighbors algorithm to identify k normal images which were closest to a test sample using only the image level feature representations. So on the right side, I have shown that, okay, we are taking the features of the neighbors and we are storing them. And it basically tries to figure out, okay, what are the k normal images that are closest to my representation using the L squared norm, um, mean of that. And basically it's trying to come up with a metric for k nearest neighbors. So it's trying to select k total subs k total subs a subset of basically the normal features. Um, and once those k features have been selected for for the image level image level k near knn, then a gallery of features at the pixel level was constructed using the nearest k normal images. So in this case, we now also have basically differences between the pixel level representation and the image level representation. In the pixel level, we have last m levels. So the pixel level representations are then a gallery of features is created for the pixel level feature representations from the extracted k normal images. And subsequently, another k nearest neighbor is performed in order to find the and in order to perform segmentation of the anomalies. So subsequently, pixel level KNN was performed to segment the anomalies. So in this case, we can say on the right side that the small k in the bottom equation is basically a different different k nearest neighbors that's basically being used for pixel level segmentation. So that's basically just an overview of the method. It's a very simple method, but it just uses two levels of KNN and two different feature representations.
But the feature extraction step, they have a pre-trained ResNet, right? And
Yes, yes.
uh, at pixel level performed by concatenating features from the last m levels.
Hmm.
But what additional components were added to the pre-trained ResNet? Or it's
Um,
just they just run the pre-trained ResNet to get the features.
yes, yes. I think that's a good point. So it's just running the pre-trained ResNet to get the features and
Use
no
KNN
additional.
to okay.
Yes,
So there's no explicit training.
there is no explicit training for this. So that is where it's just using the pre-training aspects and not having a training time cost. So that is there, yes.
Interesting. Okay. Well,
So it's basically taking the pre-trained representations. And I just wanted to show a few images basically so that we get uh, uh, basically the intuition for it. So on the left side, I basically have an anomalous image. This is taken from the article on Spade.
mhm.
And the second one is the retrieved top normal neighbor image. So this is basically coming from the k nearest neighbor search. The third one is basically the mask predicted by Spade, basically based on the differences that we observe. So this is just the mask that is being predicted. That's the segmentation mask that's being predicted. And
So how
uh,
how does this method know the uh so that's you said that hey the spade will use opportunity ResNet to generate feature representation for the
yes, yes.
is this feature representation for used for every pixel?
Yes, yes. So I think that's a good point because it has a different representation in order to segment anomalies at the pixel level. And first, basically, it uses the image level feature representations to come up with the k images.
Mhm.
Then it basically does another k nearest neighbor search, a smaller search on just uh, the normal images that were extracted from the image level KNN. And then based on that, it basically tries to figure out if a pixel is anomalous or not based on the pixel level representation. So I will just go to the previous slide. So in this case, the lower equation is basically saying that, okay, I take the big F form a normal image and at a specific pixel, and I use my present pixel level representation, and I use
Mhm.
a different k for doing a k nearest neighbor search at the pixel level for every test sample. So that's basically to reduce the cost of doing the KNN, because pixels can be very large in the image, and uh, if we do it over all the training set, that can be expensive. So that's where.
This is like hierarchical clustering.
Yes, yes, I think that's basically the idea. I think basically first to do one level of KNN, then the second level of KNN, which is totally different at the
Okay.
pixel level.
Okay. Let's move to the next work.
Yes, yes, let's move. Okay. So I think that's the first article on Spade. The second article, which is patch core, with that is also basically method, which is basically trying to do a k nearest neighbor type search. It's totally unsupervised, and it's trying to come up with a little bit of an improvement on the previous method, and it's motivated by the very high numbers that were observed from the pre-trained network representations, particularly. And in this case, the patch core network, what in addition to the previous article, it uses a neighborhood aware patch features. So neighborhood aware patch features is where it's a little bit different to create a core set subsampled memory bank. And the process of creating a memory bank can be summarized as follows. The first stage, basically, in the first stage, it extracted intermediate to mid level features, only the intermediate to mid level features, not the features that could be very general to ImageNet. So it says that, okay, the last few layers can be very ImageNet specific. So I just take the intermediate ones from a network that is pre trained on ImageNet. Features deeper in the hierarchy were avoided to ensure that the features were not very specific to ImageNet. And for any given patch location, so also it basically another difference is that it basically divides the image into various patches based on the intermediate level, based on the highest resolution that is observed in the particular layer of the pre-trained network that we are trying to extract. So because as we keep going down the deeper through the network hierarchy, the basically the resolutions basically start changing. So we start getting the downsampled representations, which for the networks which are trained on a classification task for ImageNet. So in this case, therefore, the highest resolution that's taken is basically the patches in the image are divided based on the highest resolution, that feature resolution that's taken from the network, a convolutional network. And for any given patch locations, features obtained were aggregated using global average pooling to obtain a neighborhood aware representation. So what it basically does is that, okay, I have my features which are in the form of patch locations, and let's say my image is h cross w, then I only take like a few neighboring patches, and I basically do a global average pooling of the features in order to come up with another single feature representation for every patch. So that's where it's a little bit different. So that's where it says, okay, I'm trying to be neighborhood aware, um, and that's where the feature representations are a little different. And a feature bank was created using patch representations from every training sample. We get these features, and once we get these features, of course these features can be from different layers which can be concatenated or aggregated in a different way. And the obtained features, once they are obtained, and these are basically obtained at a patch level, So these are like a lot of vectors that are collected at patch, a lot of these patch features that are collected. And once we have these patch features for all of the training samples, then we course set some sample them to come up at a reduced memory bank. And course set subsampling is where it is a little bit different. Also, the core set sampling task in this case, where it tries to perform a reduction of the memory, like 10%, I'm just going to retain 10% or 1% of the features. That was performed in a greedy manner because the mathematical equation that they had to do the exact one could not be, basically, that was not feasible. So it was done in a also done in a greedy manner, which was approximate. And at test time, the method used the nearest patch feature in the memory bank to perform image level and patch level segmentation. So in this case, they are doing a patch level as opposed to a pixel level. So the image level and patch level segmentation was done using the nearest neighbor search. And of course, I think it's being used as a benchmark for almost main of most of the articles on anomaly detection. So that's basically a feature for it. And
How does it do like a patch segmentation? It's basically like mark the whole patch as like it's still like a binary classification, right? But it's gonna pre mark the whole patch as positive or whole patch as negative.
yes, yes, so it basically comes up at a patch level segmentation, and then it tries to basically use, I think it also does a little bit of smoothing, but it also then upsamples the patch level representation to come up at with a pixel level segmentation. So I think that's done bilinearly. So so that is where it basically first classifies every patch, as I think we are discussing, and then it basically upsamples it. So that's where it's a little bit different. So
But
and
if that's I think that's a little bit to me a little bit that's a little bit confusing because you want to detect anomalies, right? Normally,
mhm.
it's not necessary the anomaly, say a crack, will be exactly inside a patch, right? It might go across different patches.
Yes, yes. So I think
How
that's
does
a
it,
good.
Mhm.
Mhm.
How does this paper address the issue here?
Yes, so basically the point that it does, the way it does is that it does a classification at the patch level. So first it basically we have a grid of patches on the image. So let's say the image was 256 by 256, then I say that okay, every 4 cross 4 pixel is basically my patch, and so then I get like a 16, I think in this case 64 by 64 patch level gridded representation. And for every patch, it basically gets the for a test sample, it will get a representation, feature representation from the pre-trained network, and then at a patch level, it will try to do a classification using the core set subsampled memory bank, which is basically created unsupervised from the normal training data. So that is where it's basically trying to do classification at a patch level. And so if of course if different patches are anomalous, then it will mark all of the patches as anomalous, like nearby patches, and then come up with the upsampled segmentation of the pixels. But I think that's a good point, that if the basically the crack is only within a patch in within a very localized area, then should it try to do a multi-scale search in that case, like a multi-sized patch? So or maybe come up with different image sizes. But I think in this case, the patch size is decided. I am very sure that the patch size is decided from the patch size is decided from the highest resolution in the feature hierarchy of the pre-trained network. So that's where it's coming from. And I think do have an image for it. So I mean, if it becomes a little bit more
Okay.
uh, better from here, because the previous one didn't show any image. So the nominal samples in this case are passed through the pre-trained encoder, and we do again a neighborhood aware, locally aware patch features. We get like average
Oh,
value,
I
which
see,
is
I
a
see, I see. Yeah, this
black.
the figure is much more clear. So
Yeah.
basically, yeah, it use features, and then when it extract the patch features, then do core set sampling.
Yes,
That's
yes. So
pretty
the
much.
core set sampling, yes.
And then do the nearest neighbor search. Okay. Do you have to assume that your, I don't know, maybe like when you portray a network on ImageNet, they're gonna have some similar representation for cracks or for, um, okay. Yeah, let's go ahead.
I think that's a good point for few short scenarios. How can it work? So, and it is basically a little bit unsupervised here, and here it's basically doing the similar thing as k nearest neighbor for spade. So,
Okay.
um, and okay, so I'll go to the next one. So that was basically patch core. Of course, it's a little bit condensed representation. So I will go to the next one then.
Oh, this is also the patch core?
This is a different article now. So this is segmentation based deep learning approach for surface defect detection. So I'll also make sure to add the year for this in the in every slide so that the year is
Where do
visible.
these papers, where are these papers published?
I think that's a good point. So the patch core one, I think it was either in 21 or 22. I think possibly in 21, I think. This one was before patch core, but I wanted to go over the those ones which were quite specific. So this is, I think, 2019 paper, right? 2019 or 20 paper, 2020 paper, I think, before that. So
Okay.
uh, yes, so that's a good point. Actually, I'll try to address that. And it in this case, it basically. So I'll also make a point that there is basically research that's focused on anomaly detection. Basically mainstream work that's coming like Patch Core, Spade, and a lot of other articles, few short. And there is a different paradigm or different. I think maybe peer review or other types basically that are coming from the surface defect detection. So the surface defect detection becomes a little bit different domain as compared to anomaly detection. But
Okay.
this, yes, yes. But the approach is very. I think they are applicable both ways. And in this case, basically, they came up with a new anomaly detection dataset which contained defective electrical commutators called collector SDD. I haven't added the full. It's not a very large data set as the MB but it's for surface inspection.
Okay.
And it basically used a two-stage convolutional neural network to simultaneously perform defect segmentation and classification. And the segmentation output was basically used to guide the classification. I'll show the image basically. Um, and although the approach produced pixel-wise segmentation results, it did not assess the pixel-wise accuracy. So it didn't come up with the pixel-wise AUROC score. It only basically reported the image level detection metrics.
This is a
And
supervised learning approach.
um,
The supervised learning.
I'll confirm that basically if it's a fully supervised approach or not. I think that should be supervised because it's directly using the CNN to do the segmentation. So, um, and also, I think, yes, I think it should be supervised because it included defective samples in the training data set. So it's not an unsupervised approach. So so unsupervised is not the case, I think.
So
Okay, so
the classification means that it's gonna classify whether this is a commutator has is defective or not, right?
yes, yes, I think that's a good point. So basically, the pixel-wise task is to come up with a segmentation totally. In this case, it's only doing an image level detection. So at the image level, if the full image is defective or not. So that's where it is um, using the output. And I think that there were a few articles which said that, okay, and I remember that in this case, also the loss function was composed of two components, which was the segmentation loss and the classification loss. And basically, the segmentation loss was coming from the anomaly mask, and I think the classification loss was coming from the ground truth anomaly data. If it's a full image level, cross entropy loss, if it's basically classified as anomalous or normal against the ground truth detection result. So
Yeah, so
uh,
basically the segmentation should be just a pixel-wise classification, right?
yes, yes. So the segmentation should be pixel-wise classification, but it said that, okay, it did not give the pixel-wise accuracy scores in this case,
Okay.
as I remember. Yes.
Yeah, let's move to the next paper. This is too old. Yeah.
Yes. So I will also say that there are a few articles which are basically trying to use the generative adversarial paradigm in order to do anomaly detection. And in this case, I think one of the papers, which is ANOGAN, which tries to use an adversarially trained encoder to map the distribution of the normal data to a latent space.
Hmm.
And at test time, it basically, first of all, it basically tries to map the distribution of the normal data to the latent space. So uh, uh, given some arbitrary random input, it tries to construct an image and comes up with a loss, which is the normal discriminator loss and the generator loss. And at test time, the key difference here is, as compared to other generative approaches, is that it tries to perform a reconstruction of the test image in the latent space using another loss function. And both the discriminator and the reconstruction and the discriminator loss were used to basically identify and segment anomalies in this case. And it performed the experiments on the retinal OCT dataset, and that's basically the other biomedical data set that I was showing in the slides. And so the only main difference here is that the similar main difference is that, okay, first thing is that, okay, it does the normal adversarial training, but the difference comes from doing the reconstruction in the latent space and coming up with the difference um, uh, of the test image in the latent space. So that's where it is a little bit different. So
But how, I mean, in the latent space, if you use
mhm,
GAN, I mean, original GAN is to map some noise, like Gaussian noise to
mhm.
after some kind of transformation, right? You're assuming your transform the object should follow some given data distribution, right? So here I'm kind of confused. Like you adversarial train an encoder to map the distribution of the normal data to a latent space,
Okay.
and then how does it perform segmentation and also anomaly detection?
Yes, yes, I think that's a good point. So, one of the things I did see was in the loss function, it tried to reconstruct um, in the latent space. And then I will check if what would be the exact metric that it was using in order to basically segment the anomalies. So that's a good point, and I'll add it here. Um, and so it did the reconstruction. So Would you like to go over the article here in this case, or should I?
Yeah, maybe you can quickly, pull out the paper and we can take a look at the formula, so we can figure out, what's their key idea.
Yes, yes. I'll basically open the article and so this is the N again. I'll directly go over the method, skipping the main parts.
I can't see the paper. I still see the slides.
Yes, I will just share the paper. Um, I'll share the screen again.
Okay.
So I just shared the paper. Can you see the paper?
Yeah, yeah, I'm looking at it now.
Yes, so I think I highlighted a few points here. So I'll not go over that. I'll just go over the metrics. So this is where it does the training. So the training loss is basically very similar to normal adversarial training. Basically, um, the samples are in the latent space, that is just a normal random sample that's taken 1D vectors of uniformly distributed input noise, and it tries to create 2D images from an encoder using the adversarial loss. And of course, we have the normal adversarial training of real samples and fake samples with a discriminator.
Mhm.
And of course, it is just trying to basically some of the explain the adversarial loss here.
Yeah, this is still the GAN, right?
Yes, so this is basically the normal adversarial training where it says, okay, the generator improves in generating realistic images, but the discriminator progresses in correctly identifying real and generated images. So that's the training part. So not many differences here. In terms of, I think that's where the difference is basically where it tries to map new images to the latent space. And
Reverse image.
yes, yes, I think that's the reversed image basically. So, okay, so that's where what it tries to do is basically by first doing a reconstruction of the basically doing a inversion in the latent space. It then basically does a reconstruction of the image and from the encoder, and then it basically measures the residual loss, where it says, okay, the residual loss measures the visual dissimilarity between the query image X, that's the test sample, and the generated image D of Z gamma, which is basically generated from the latent sample, or basically the projected sample in the latent space that was closest to the test sample.
How is Z gamma um from is gen get?
Yes, so I think that's a good point. So what it does is it's basically saying it over here that to find the best Z,
Mhm.
we start with randomly sampling Z1 from the latent space and feed it in the trained generator to get the generated image. Okay, so in this case, the loss function, this is a part of the loss function in this case. So that's the
Oh,
residual
so they
loss.
minimize this loss to find out the image is actually the noise for X, right?
Yes, yes. So that's where I think that's the loss basically. That's the
Okay.
minimization that's coming from. So
Now, once they get this residual loss, what were they doing?
Yes, so this would be the residual loss, and there is also, I remember, definitely a discriminative loss where they added a discriminator in order to
Uh-huh.
use the discriminator for classification of the generated image and to make sure that it's as realistic as possible. Okay, so here it's basically making a difference first. So one is that, okay, you could either use the discriminator loss, and basically then it's basically coming up with the yes, so that's where it's a little bit different. So this is a little bit specific to the article, but the motivation is still the same. So one could either use just the discriminator loss in the loss function plus the reconstruction loss, but one could also use, basically they were using a feature matching that I've also seen in some of the other articles, where it basically takes the features of the discriminator, it takes the features of the discriminator of the test sample and the generated latent sample, and then it tries to basically minimize the differences of the discriminator features. So that's where it tries
Uh,
to say yes.
what's F? F is a discriminator? F is not a discriminator, right? What is F?
The F would basically be a layer, intermediate layer of the discriminator. So it says
Okay.
yes, it's intermediate layer of the discriminator. Or in the general case, usually I think it's just the discriminator loss that's taken for image in painting, for example. But here they had a different feature representation being used, and this is the complete loss basically. In this case, the discriminator loss is modified in order to do the training, and the coefficients z, only the coefficients z, so we are trying to do a reconstruction in the latent space, so that's where it's trying to back propagate. So uh, adjust the z based on the gradients of the loss.
Okay. So once they get the Z gamma, what are used to? Oh, so okay. Uh, so they can optimize Z gamma for every example.
Yes, so basically given basically for every test sample they will first find a z gamma in the latent space by minimizing the loss,
Uh-huh.
and then they will identify the anomalies based on the reconstruction and the discriminator uh, score that were basically coming. Here it says, okay, it's just the residual loss and the discriminator loss. So
AX, X, okay, X is the image. RX, what's RX? RX is the
Rx would be the basically the residual score. I think that should be in the latent space. So that's where it says, okay, the residual score, then the residual score is simply the residual loss in the latent space that was basically coming from the reconstruction. Uh, so the
yeah. So can you can you,
reconstruction,
can you just go up? I mean, look at previous. Yeah, yeah. This LD Z gamma. Okay, go on. What is R?
yes, so this one is basically the LR. So it's the basically reconstructed image from the reconstructed image that's coming from the latent sample by passing it through the encoder. So by
But
passing
but
it
but,
through the
but
generator.
they have to first solve Z gamma, right?
Yes, so that's where it basically first try to optimize the loss based on the Z gamma. But it also says that the residual score and the discriminator score is at the last update iteration of the mapping procedure to the latent space respectively. So that's where it's, I think, directly taking the residual loss and the discriminator loss for anomalies at the last iteration only, I think.
Let me try to read this. Like our loss function
Mhm.
used for mapping to the latent space evaluates in every iteration gamma. The compatibility of the generated image GZ gamma with images seen during adversarial training. Thus, anomaly score which expresses a filter query the model of normal image
Mhm.
can be directly derived from mapping.
So it's basically just the weighted sum of the residual score and the discriminator score. But it says where the residual score and the discriminator score are defined by the residual loss and the discrimination loss at the last update iteration uh, of the mapping procedure. So
So basically, the RX is actually the LRZB gamma, which is uh, the last equation, like equation five. Equation five, I think in the previous page, right?
yes, so Rx, I think the LRZ gamma would basically be the LRZ gamma here, and the LRZ gamma would just be the reconstruction loss from the latent sample.
Yeah.
But mhm.
And can you go to the equation five?
Oh, okay. I think I was at a question. Oh,
And
sorry.
LPZ gamma. Okay. Oh, I
I
see. I see.
think
So basically, their score is just when you're solving equation five, what's the value?
I think that's a good point. So it's just that in the while doing the experiment, we just keep getting those loss scores. I think that it maybe it's just taking the loss value and trying to come up with the anomaly score from there. So um, I think
So once
that
once they got this score, they're gonna rank all the examples and pick up the largest score or whatever. How do
pick up.
they leverage this score to find the anomalies?
So that's a good point. So I think this one is just coming from the last iteration of the mapping procedure. So just the very last score that we got from the training
Mhm.
at the last gamma iteration.
So the model uses a large anomaly score for anomalous images.
Yes, yes. So basically, if the reconstruction loss is very
Oh, I see.
high,
I see. Okay. So basically, for the test images, you just throw this and solve equation five and see eventually what's their value. That's the normalization score, right?
I
Anomaly
think
score. Yeah.
I think that should be the best way to talk about it because they have just rewritten, I think, the same loss value here, I think. So
Yeah, if you look at equation five, can you go to the equation
one
five?
minus, yes, I think it's very similar. It's just one minus lambda and lambda here. So
Yeah.
yes,
Equation five. So basically, they're just doing like backpropagation to minimize this guy, right? And then they look at the final iteration. What's what's the LZ gamma? What's the LZ gamma is? They use it as the anomaly score.
yes. So basically, I think it's just a very crude way of basically doing it. Maybe just taking the
But this
loss
is just
value.
to detect uh, different images. This is not like a segmentation. There's no
Uh,
segmentation here. This is just to show, like say you have like 100 images, one or two images are not, um, one or two images are not are anomaly for others. Like you have 100 cats, then you have a dog, and then the dog's anomaly score will be the highest, the largest one.
I think so. It might depend on basically whether L is actually. I think L should be a loss value, and I think definitely I think it should just be at the level at that particular level. So um,
Yeah, for equation five, yeah, because it uses a generative model, right? They use GAN uh to they train again to get a generator, right? And then they essentially trying to like throw a new image through my trained model and say what is the score. if your model, if the model, if this new image doesn't very well fit the generation process of again, that means this guy, this new image, it could be an anomaly. That's the key idea.
Yes, and I think that is where it is also saying that we use the anomaly score for image-based anomaly detection, that if a full sample is anomalous.
Yeah.
And I think for segmentation, it's basically coming up with the residual image for identification of anomalous regions based on the reconstruction loss per pixel, I think, based on the
From
reconstructed image.
from the paper here, I can't see any segmentation step here. They just throw the whole image, the query image X, into this score and say how in what kind of degree we can view this is an anomaly image.
Yes, so
And
I think
it just
that's
like 2D image patches. Okay. Yeah, maybe this is the way they find the small patches. Like you can partition the patches, partition the images into a lot of
mm,
like small patches and train again for this. Then at least you can detect which patch is a anomaly.
yes, I think there can be a lot of scope of improvement, I think, on it, and how the patches are done, and because it's basically just taking the residual image later and trying to see if the patch is anomalous or not. So um, I think that there can be just as we have already discussed that okay, it's just the last loss value or just the residual score per patch. So
Okay.
I think that can be a good way of thinking about it because there are like a lot of improvements that have come up also, so they can be modified for GAN maybe. So uh,
Yeah. Yeah. Let's continue. Let's talk about.
yes, yes. So I will. I think I'll try to first share it again, so
Yeah.
that
Go back to the slides again.
okay. So can you see my screen? I just
Yes.
okay. Let me. Yes.
Okay. Can move to the next.
So I have some basically some high, some very coarsely written articles because I thought they might be a little bit good to mention. Which is this one basically, which tries to. And so in normal autoencoder training, they said that okay, I'll use the L2, that is the least squares loss per pixel to perform a segmentation and or basically come up with a metric. So in this case, it says that the pixel-wise L2 loss, while training the autoencoder, it does not model dependencies between the pixel. I'm sorry for the spelling. And hence, a more robust loss is needed for autoencoder training and evaluation. And in this way, it basically uses a structural similarity function, which takes in the intensity values and other contrast, brightness, etc., with the neighboring pixels so that the pixels are modeled. So there is a little bit of a dependence basically in the loss between the pixels. And it's basically trying to get okay, what are the structures structurally, how different is the image from the uh, from the from the input image. So that's where it tries to improve the normal and autoencoder training, but it's still fully unsupervised method with the autoencoder. So there is no supervision.
How is autoencoder working in unsupervised segmentation? Autoencoder is just to generate a low rank representation of the image, right?
So the autoencoder will have basically, I think, definitely a latent space where it then generates basically a very reduced representation.
Hmm.
but then it will also reconstruct the image from the projected or the low dimensional image from the uh, I think from the latent space, and it will say that okay, under the restriction of my latent space and under basically the autoencoder acts as a regularizer, so the output image basically can will be different from the input image, and under that restriction how different my input image is from the reconstruction, and based on that it does the autoencoder training for the unsupervised case, based on it can be just the L squared loss or
Yeah,
um,
that's the training of autoencoder. I mean, what's the autoencoder's role in segmentation or um, anomaly detection?
in the anomaly detection case, once we have a trained autoencoder, then we pass the input image through the autoencoder. Now, the autoencoder has been trained on the normal samples because the anomalous samples were not available during the unsupervised training. So the normal samples, it assumes there is a big assumption. There is a very big assumption that okay, because it is only trained on the normal samples, then it should not be able to. It hasn't seen the
Okay.
abnormalities in the
So it's
image.
still like comparing with the embeddings, right? The autoencoder, after doing autoencoder, you have some like a low rank representation, right? You just look at whether an image, its low rank representation is different from, it's quite different from the uh, low rank representations in the training set.
I think that's a very important point. The I think that might basically become a different another approach basically for the segmentation of or for the detection of anomalies, basically using the latent space of the autoencoder in order to do defect segmentation and defect classification, but I mean, or image level detection. But I think in this case, the point that they're making is that okay, I pass the input image and then I reconstruct the input image, and once I get the reconstruction, then I try to take the differences. But I think that's a very good point. A different approach could be just trying to check what is the feature wise dissimilarity at the latent space or the feature wise dissimilarity at other layers as compared to the normal
Okay,
samples.
so one, okay, I think the point here. So I mean, after reconstruction, you take the difference, pixel-wise difference, and then how to,
And basically based on a specific threshold that is set, we can basically figure out if the pixel is basically anomalous or not. Um, so that's
oh,
where
does it work? That's a that's very interesting. So basically, you run autoencoder and you got to reconstruct the image. You just do the pixel-wise difference between the original image and the reconstructed image, right? And then look at the difference threshold. If the threshold is big enough, and then we can reveal like such a pixel is represents some defected regions.
yes, so based on the pixel wise differences, it tries to come up with the pixel wise classification for defect segmentation. So and based on setting up a threshold, it can be the least squares, just taking the features of the reconstructed image and basically the channels and trying to measure the difference,
Mm-hmm.
or it could be a structural similarity function which is used in this case. And I think there are few articles before this article, so I wanted to basically just include the main one. So basically just uses the structural similarity function instead of the L2, the normal pixel wise L2 function, to find out a defective pixel, or whether it's a defective pixel or not, to classify if it's a defective pixel.
Okay. Yeah. Yeah. Go ahead.
and
Mhm.
And yes, I think you also made a good point, but it also is a point, as you have said, that if it works or not, that okay, a lot of the times the network training we try to generalize. Basically, we try to generalize a little bit from the data, training data. So because it tries to generalize, sometimes it reconstructs the anomalies well. So that's a little bit of a drawback in here. Um, So instead of the autoencoder, basically this particular article. So this was I think I basically included this article because it was using a variational autoencoder. But in the introduction, basically it said something different, that it should use the latent space. And then in the conclusion, it said something different, that we should not use the latent space. So there was a lot of dissimilarity in the article. So I just tried to basically make a mark that okay, this was trying to use the variational autoencoder and trying to check anomalous areas, either based on the reconstruction or based on the latent space. So, but it was a little bit ambiguous article. So, but it used the ELBO laws for autoencoder training. So I just wanted to um, add that here.
But
So
this is mainly for anomaly detection, right? So if some anomaly image comes here, they should be have like a very different elbow loss.
yes, yes. So the ELBO and the KL divergence based metrics or the reconstruction based metrics. So
Yeah.
that's something.
Okay.
So there, I will also make a point that there were other articles on autoencoder and VAEs that I have collected. So I'll also add those. So this is a little bit 2020 research right now. So this was one of the articles that did some of the novelty detection task on a brain MRI data set. And it basically described a lot of different metrics which could be used in order to do novelty detection with variational autoencoders. And it basically came up with a lot of metrics. So I haven't written down those metrics, but it tried to use the expectations in the latent space. It tried to use a reconstruction based metrics, and it came up with a full stochastic reconstruction, for example, using the posterior and the conditional data distribution that was learned through the encoder and the decoder. So basically the article was very emphasized towards how we could use the variational autoencoders for novelty detection and what are the different metrics that we could generate. So this is where I thought that maybe the variational autoencoder part is a little bit less explored for anomaly detection. So that
So
is
basically, they use the variational distribution for the latent space vectors to represent those images, right? And then they just define some metrics according to this learned distribution and to identify which images could be anomalies.
yes, and in this case, I think it came up with a lot of metrics, and I think, as we have discussed, that it used the encoder for learning the posterior distribution and the decoder, as you had also explained in class, that okay, it's using the encoder for the posterior of the latent sample and decoder for the uh, posterior of the data, basically P of x given z, so Q of x given z. So and it basically comes up with the ELBO loss, and based on that, basically there's a summation in the loss function that comes from the independence and um, basically from the simplification, and then it basically, after training it using the VAE training, it basically comes up with several metrics, basically using the learned posterior and the learned conditional data, basically the learned posterior of the data. So P of x given z. So from there, it said that okay, we could use the VAE regularizer as my loss function, because I'm stating okay, my P of z is a prior, and I'm learning basically a Q of z given x, which is a posterior, and what is the KL divergence
Yeah, I
between
know.
the.
Yeah, I know that. I know you don't need to explain. I'm very familiar with that version of it. Yeah, go on. Go to the next. Yeah.
Yes, I'm sure. I think you are already very, very well versed on this. So, So this is one of the articles that basically came up with very, very good metrics on the specific MVTech data set, on the anomaly detection data set, and basically a stepping stone, which is very cited. Um, and it basically comes up with a patch distribution modeling framework for anomaly detection and localization. Um, and it extends some of the prior work which was there in order to do patch wise anomaly detection. And it basically extracted patch level feature vectors from different layers of a pre-trained CNN. That is where, first of all, it tries to use representation learning from a pre-trained network which has been trained on a large image network, and it is a fully unsupervised approach in that way. And it doesn't have any particular training aspect for the CNN, but it has a training aspect for the Gaussian distribution training. So then there is another aspect to it. It basically makes a point that I'm trying to concatenate the feature vectors that I've obtained from different layers of a CNN. So some of the articles basically in this area also just try to use one particular feature layer. But this basically made a difference by saying that I am going to take different layers of a CNN, and then I'm trying to going to construct a concatenated feature vector based on the different resolutions that I'm obtaining. And I'm either upsampling them or just using the same feature from the different layers. And the concatenated features obtained from the normal training samples were used to calculate the sorry from the to calculate the mean and the covariance metrics for every patch. So now I have basically concatenated feature vectors for the entire for every patch in the image, plus I have it for all the training samples. So using the patch level representation at a particular patch from the entire training sample, all the training samples, I calculate the mean, I calculate the covariance matrix between my feature dimensions, and of course, the covariance was calculated between the different dimensionalities of the feature vectors of every patch, and the feature vectors include different semantic levels of a CNN. It's a hierarchical representation. And basically, the method therefore models a Gaussian distribution for every patch vector using hierarchical features obtained from a pre-trained CNN.
So this Gaussian distribution is I'm a little bit confused here. Like, so you got every patch. For every patch you can extract a set of features, right? So you're gonna concatenate all the features into one long feature vector, and
Yes,
then get a Gaussian.
yes. And then we get a Gaussian
But this
plus.
Gaussian is a scalar Gaussian, right? You got a mean, you calculate the variance, or what?
Yes, yes. So it would basically be a mean vector for every patch, and there would be a covariance matrix for every patch. So
But
the
if you have a
Gaussian,
mean vector, that means you should have like multiple feature vectors for a patch, right?
yes. So in that case, basically it would be multiple feature vectors for every patch, and the covariance matrix for the complete for the so that would be basically a matrix of d by d if d is the dimensionality of the patch feature.
And then how do you detect whether a patch is anomaly or not?
I think that's a good point. How is anomaly detection performed? The anomaly detection is basically performed using the Mahalanobis distance metric,
Oh,
which so let me check if I have it in the other slide. So in this case, it says that at test time, the Mahalanobis distance was used as a metric, and the Mahalanobis distance is basically x minus mu transpose sigma inverse x minus mu, where mu is the patch level mean feature that I have obtained from the representative normal samples. The covariance matrix is simply the d by d covariance matrix, and and basically it's using the distance metric, the Gaussian distance matrix, which is basically a very famed metric, the Mahalanobis distance, that's being used for segmenting anomalies. And here I have also added the picture. Basically takes n normal samples, and for every, basically here a red colored patch, it gets the feature representations, and then it gets the mean and the variance for every patch. So it's basically a lot of boxes. These boxes are just the means and basically the parameters for the patch, so which are
Oh,
used
so
to
oh, okay,
do.
okay. Okay, this one is more clear. So it's basically you got n images. That's why you got n vectors. And so you can compute the Gaussian distribution for patch. That's the
Mhm.
patch distribution across the training set, right? And then
That's the patch. This, yes, yes.
and then you want to test a batch, and in a new image, you can just calculate the Mahala Mahalanobis distance, right?
Yes, yes. And for any given test sample based on the mean and the covariance, I and the so basically, as you we have said that it's basically a scalar that's coming from the Gaussian distribution. So the
Yeah, that's
scalar is,
correspond to the log Gaussian density. You just
yes, yes.
yeah, you throw them into a Gaussian distribution and evaluate the likelihood, but you take a logarithm.
Yes, yes. So it's just the likelihood, and basically just taking the log of the density, negative log of the density, we get the distance metric in this case.
I see.
And one thing that could be very, very crucial, I think it was in the earlier slide, which could be quite good, is that it also tried to do dimensionality reduction on the patch features. So, it was extracting the features from different layers of the CNN,
Uh-huh.
and it was trying to experiment with the dimensionality reduction, either random dimensionality reduction or a principal components analysis with
Mm-hmm.
the highest variance features being selected. But it said that when it did the random dimensionality reduction, that is just randomly selecting any feature from the feature big feature vector, that actually led to better score as compared to a principal component analysis. And it said that, okay, this confirmed that for localization and detection, the highest variance features in the principal components were not discriminating between the normal and the anomalous classes. So that was like a little bit, uh, I think, a little bit weird observation from the uh, articles on using the Gaussian distribution based metrics. So
Yeah, I'm thinking of uh, when they do this, they have to ensure the training set doesn't include many anomaly instances, right? Otherwise, the Gaussian distribution will be very easily distorted because Gaussian distribution is very sensitive to anomalies.
I think that's a good point, because the main point for it is that it's doing a full unsupervised learning. So the mean and the covariance are used to learn the distribution of the normal features. So we are trying to learn, okay, what is the distribution of the normal data that we are getting from the training set by approximating it with a Gaussian for every patch. So every patch distribution, for any normal image, every patch distribution is approximated as a Gaussian distribution for the normal, and it's doing this approximation for normal data. It's not including the anomalous sample to approximate it. And at test time, it says that, okay, my anomalous sample should be at the tail of my one of the some of the tails of my learned Gaussian distribution. So it shouldn't be in the peak end portions. Uh, so that's where it basically uses the distance metric, the negative logarithm, to find
Yeah.
out if
As my point is like one slight
improvement over this is that suppose I just collect random data set, right? Even don't know whether it contains anomalies or not.
Mm-hmm.
Probably we should use like a student t distribution. We should estimate student t distribution, right?
I think that's a great point actually.
Yeah,
Uh,
and then when we have a new query patch, we can still evaluate whether the likelihood is at the tail, right? But it doesn't alter the main shape uh, of the distribution because for student t, even you have many anomalies, it won't like distort the whole density a lot.
I think that's a very good point because I was also thinking that okay, if a different distribution can work, but I think that the idea of student T is I think the best one, which I think you have given. So I think I can experiment if the student T distribution gives a because it's heavy tailed also. So
Yeah, yeah.
uh, so
Yeah, if
that's
it's
just a
like a
good.
PADM, PADIM, this method is kind of like very effective, or it's kind of like state of art.
Yes, yes. So it turns out that basically just by doing the normal Gaussian approximation, they got a very good score on it. So
Oh, okay.
it's very highly. I think they are just using the pattern result in all the result section, even the 24 articles. So I think this is a 22 article, 2022.
Okay.
Um, so it's
Where
still
is it published?
very.
Where is it published?
I think it was 2022, but I can confirm it exactly if you would like. I can go to the article now itself
Okay.
and just confirm it.
I'm interested. Is it like published in CVPR, ICCV, or biomedical?
Let me take a look. It should be Padim, right? Yes. Oh, it's 2020. Sorry, it's 2020. I'm 2 years back. So it's basically a 2020 November 2020, which I think this was taken from Archive, but I can check if a publication is available now itself. Uh,
Oh, it's a highly influential paper. So citation is almost 1,000. Oh, it's ICPR. Okay.
okay, I think you have already taken a look at it.
Yeah, okay. ICPR is not like very top venues, but this paper is very influential.
Yes, that's very influential. So you have observed it from the hair, basically. I was just wondering how to get or if I should just do a search and try to figure out.
Just the search in Google Scholar, it will pop up.
Oh, okay. So you have already searched it in. Okay, okay. I thought maybe.
Yeah.
Okay, okay. So that's 2020, but it's still very recent, basically. So, and I think, as you're saying, it's very cited also, I think.
Yeah, it's a citation is approaching like 1,000.
Okay.
It's crazy.
So huge. Maybe we get the same with student T distribution. So that would be great.
Okay, that's a kind of like a trick. I mean, testing we can do, right? It's simple, but maybe it's a good starting point for us. Yeah. Yeah. Next paper.
Hmm. So that would be this one, and so I'll just go to the next one.
We can skip this one. We have yeah.
So this is another article which basically use the multivariate Gaussian assumption. So there were a few articles, three articles basically, which I checked out, which use the multivariate Gaussian assumption, but they try to model the features a little bit differently. The features in this case were extracted from a specific level of a pre-trained network and not various semantic levels. And average pooling was used at the specific level to obtain a one-dimensional feature vector.
Okay.
So in this case, what they did was they didn't have patch level feature representation.
Mm-hmm.
And in the previous PADIM case, they had a patch level feature representation, but in this case, they just had a feature representation that was a single vector at a particular level um, for the image. And again, the Mahalanobis distance, that the Gaussian distance metric was used to calculate the mean and the covariance of this feature vector from the training data. And but it had the feature engineering part was very different in this case. It didn't have patch level features. It didn't have features from different semantic levels aggregated in order to calculate the mean and the covariance, but only one specific level. And it still used different levels of the pre-trained CNN, but it didn't basically do a covariance task in between all the features of the extracted network of the different semantic levels.
So
And
this is
what it
a, I mean, the features are coming from this image level. It's not pixel level.
Yes, yes. So in this case, the pixel level metrics were not reported, but it was basically using the one-dimensional feature vector to represent a full image, basically. So
Okay. Okay. Um, there's not much much more. I mean, there's no new things. There's no things brand new. Like yeah. Let's go to next.
yes, yes, there is not much of innovation here. So as I have already, I think in the previous, this basically image is just giving the same idea behind it,
Okay.
behind the words that okay, we are getting the Mahalanobis. Okay, so I will go to the next slide then. If I think it's just a sum of Mahalanobis distances at different levels that they are using. And one of the very good points that it did make was that how do we select a threshold for the Mahalanobis distance? And it said that it tried to set a working point or a threshold for the distance metric. And
Okay.
it used the argument that the Mahalanobis distance, Gaussian distance metric follows a chi-square distribution.
I square.
That
Okay. Mm-hmm.
okay, chi-square distribution for all the samples, and using the CDF of this distribution based on okay, what is my desired false positive rate, and because it's basically calculated from the normal training data,
Yeah. Yeah.
and how much false positive rate I want, I can do an inversion of the CDF, and then I can basically get the threshold based on what
Yeah.
I
Okay.
want.
Yeah. That makes sense. Yeah. That makes sense. And it's more justified.
Yes, yes, so it's just a little bit more justified on the threshold, so that was a good.
That's a good point. Yeah.
Yeah. So this is the other article which basically tried to use the Gaussian mixture model, but I will not spend more effort, my time explaining it, because it later said that the results were second best or third best as compared to the presently available approaches. So it basically used instead of using the multivariate Gaussian assumption, it used the GMM and performs approximate inference using normal data samples. It's still an unsupervised approach
Mm-hmm.
um, for patch, and I will check if there were any divergence or it could be improved in terms of the GMM. I will take a look if it could, if there are any particular specific things that could be improved, because I actually, after reading it a number of times, I came to the realization, okay, that Paradigm was doing it at different semantic levels of a CNN, and some of the others weren't doing at those different levels. And so I was just getting over the differences between these. So I will also take a look if detailed look what was actually going wrong here, because it just said that okay, it's just the second or the third best even when it used the GMM, a more I think more number of parameters with the density. So um,
Yeah. One thing so you mean like GMM is worse than just use a single multivariate Gaussian to model the patch distribution?
I will. I think that can be double check if you want. I can go over that. It said that I am very sure that it said it's the second or the third best in terms of the
I was
answers.
surprised. Yeah. I mean, theoretically speaking, your GMM should be more expressive than a single Gaussian, right?
That is where I was confused also, but I actually got to know about more differences with the multivariate Gaussian after reading it a few times.
Hmm.
So this is the article which it came up with, because the GMM there's a more more effort on building the Gaussian mixture model, and
Yeah,
uh,
I mean, there could be some issue like estimation of the number of components matters, and also how are you gonna estimate the parameters of GMM? Uh, Typically, they should use the EM algorithm. If they
yes,
don't
yes, the
use,
expectation, yes.
yeah, if they don't use DM, then the estimation will be very hard.
Yes, yes, I remember from the class that for GMM, it can also have those, uh, problems in terms of getting the solution, optimization solution for the GMM. So,
Okay.
um,
Yeah, let's go through another maybe a few slides because I will have to stop at 2:45 because I need to pick up my kids. We can find another time to continue.
yes, yes, definitely. So, this is basically an article on doing multi-resolution knowledge distillation for
Okay.
anomaly detection, and this is one of the articles that basically came up with the way to do student-teacher training, where it had a larger, fully connected, fully convolutional network and a smaller, fully convolutional network, where it basically matched the feature level representations in order to train the student network and to perform anomaly segmentation and classification. It used those maps at the at the feature layers in order to basically construct the loss.
Yeah.
And it used a combination of the cosine similarity loss and the least squares loss to match the intermediate activations of the student and the teacher networks. But the bigger part was that the AUROC scores weren't very satisfactory. It was, I think, a 2019 article. So
How does the how is the student teacher training? How can this framework perform anomaly segmentation?
I think that's a big point, because for the student teacher training, there can be differences in terms of what is the. So it assumes that a student network basically has been trained on the representations that we have obtained from the teacher on normal data. So we have only trained the student network on the normal representations that we are obtaining from the teacher network.
Mm-hmm.
And the task basically at hand in anomaly segmentation is that, okay, since student network hasn't seen the anomalous feature representations from the teacher network, the two are basically going to produce a different answer in terms of feature level. And we can upsample the features at different layers and basically combine them in order to compute an anomaly detection metric for student teacher, uh, from the point of view of knowledge distillation that has been learned only from the normal samples. So,
But
uh,
how is that large FCM? What's the FCM? Fully connect is straightforward convolution network or whatever, a fully connected network.
it's a fully convolutional network. So I
What's
will.
the I mean, how do we train FCM? How do we train small FCM?
The smaller one would basically be trained by training it first. The point would be on normal samples, obtaining the feature representations from the teacher network, um, obtaining the feature representations on the intermediate layers from the teacher network and the student network, and basically coming up with a least squares loss, just a sum of, either it could be a sum of losses or I think a different loss function based on the mismatch that occurs at the feature layers of the FCN. I will add this. I'll also add, I think, picture for it so it becomes clear.
Oh, okay. This one I'm still, I mean, this part is still not clear, but I don't have to stop right now. So why don't you just add maybe figure or whatever um, description about the key idea? Because I don't know, like, uh, the larger FCN is trained by the model, or they use some pre-trained model, and then they train a small FCN. And if they do this student teacher training as distillation, what kind of data set uh, they used for this distillation? These are something I need to understand.
I think that's a good point. Basically, how is the teacher network trained? So that
Yeah,
can
how
be
is the
if it's
teacher
the
network trained? How is the I probably this work they will train the student network, right? And
yes,
do they
yes.
use like a large? Do they use like a set of normal images to perform this knowledge distillation training? And then they extract features from both teacher network and student network to construct the representation for each image, and then detect and decide whether it is a anomaly image or not. Yeah, there's something. Yeah, we should figure out.
Yes, yes. I will make sure to do a much more detailed look on it on the multi-resolution knowledge distillation. It can be quite
Yeah,
useful also.
I'm
So,
curious to know how do they incorporate knowledge distillation framework for anomaly detection.
okay.
Yeah, but anyway, let's find another time. I don't know. Uh, are you available on tomorrow?
I'm definitely available tomorrow. I think that would be a great time. I'll just update the figures and I'll add the detail to
Yeah,
it for
let
this.
me check.
Yes.
I think tomorrow 11 I got some meeting. But perhaps like from we can start from 9 to 11
Mhm.
to finish the remaining. I guess if we can move faster, we should be able to finish all those. Yeah.
Yes, yes. And I'll also add the figure for it so it
Okay.
becomes clear. So 9 to 11. I think that works for me. So I think that should be good. Yes.
Okay. Yeah, I will just send you invite.
Yes, yes. 9 to 11. Right. Okay. Yes, I know. I think that it's a little bit busy time right now. So it's just, finals week, I think. So,
Yeah. Uh, let us use the same. I can send you. Mm, that's my. Just use this one. Should be fine.
yes. And I think it's like a lot of approaches also. So,
Yeah, that's good. That's good. I mean,
in
thanks
the
for you know making all those and that will help us like learn the frontier, learn the envelope, like in the most efficient way. Then we can work out some method.
Yes, and I was also getting some clues on like as you were saying on the UNet for bubble ML and basically
Yeah,
taking a look. So from that point of
yeah.
view
Let's
also it was great.
let's discuss about it tomorrow.
Yes, yes. I
Okay.
think that would be good.
Yeah.
Okay, thanks.
Yeah.